Hi everyone. So today we'll be discussing on the topic DSU with a rollback. So previously we had discussed on this one, offline dynamic connectivity. Yeah. So now today, as I've said, we'll be discussing on the topic DSU with a rollback. It's the standard version of this one DSU, traditional DSU, right? Usually we'll be able to undo the operation or we will be able to delete actually. Yep. Via this one rollback operation. So that's the same thing we'll be seeing within the DSU with the rollback. Let's move on with the definition part. Yep. DSU with the rollback is an advanced version of disjoint set union. It's the advanced version of the DSU, nothing but the union. Fine, as I had mentioned. Yep, that allows undoing previous union operations. What does it allow? It allows undoing the previous union operations. Yeah, that's what it does. Then it maintains a history of changes. Yep. So just yeah. It also maintains a history of changes. So this point is very important. Yeah. Whatever we undo, it will be maintained. It will be maintained actually through the history. Yeah. Through the history. So it maintains a history of changes. So we can efficiently revert to the earlier state, right? If you want to revert to the earlier states, we can do. So that's the huge advantage of making use of DSU, right? So it is useful in the offline queries, dynamic connectivity, and divide and conquer problems. Previously in the offline dynamic, this one connectivity. So we went with a DSU with a rollback. We had implemented DSU with a rollback, if you remember. Yeah. So that's one of the applications as well to make use of the DSU. It's one of the very well-known algorithms. Yeah. Traditional DSU. So I have implemented DSU like many times actually. I don't even want to take the names. I have implemented DSU hell lot of times. Yeah. So this is fine. Again, let me read this one out loudly. Just listen to this carefully so that we can move on with the algorithm explanation part. Yeah. So first thing here, DSU with the rollback is an advanced version of disjoint set union, also known as union find, that allows undoing previous union operations. Yeah. Main advantage of DSU with the rollback is nothing but it allows undoing previous union operations. It allows the delete operation basically. Yep. It maintains a history of changes. It maintains the history of changes so we can efficiently revert to the earlier states. This is one of the extreme advantages or huge advantage when it comes to DSU with the rollback. What it does, it maintains the history of changes. This is fine. So we can also efficiently revert to the earlier states. Yep. So that's one of the huge advantages. And it is useful in the offline queries, dynamic connectivity, and divide and conquer problems. Yep. So this is it for the definition part. Yep. Let me delete this one. Next, let's do one thing. Let's move on with the algorithm explanation. If everything goes well, within the algorithm explanation, we can articulate the same thing in the form of code. Yeah. So if everything goes well there, and if we get the desired output, then we can discuss the complexities for the code that we have written. First, what shall we do? So as usual, let's discuss the algorithm. Yep. Let's do that. 1 second. Yeah. So let's do one thing now. Let's move on with the algorithm or yeah, let's move on with the algorithm explanation or algorithm. So let's say, for example, we have 5 nodes. Yeah. So for the algorithm explanation, I am considering very simple example. Let's say we have 5 nodes, 1, 2, 3, 4, 5. Yep. So let's say we have 5 nodes, 1, 2, 3, 4, 5. What are the operations that we'll be going with? So these are the operations that we'll be performing. Just for the example sake, you can just take the different example and go with the algorithm. So I'll just explain with a simple example. Yeah. So here we will be going with the 4 operations. One is union, union of 1, 2, this one, this edge actually, union of 2, 3, the second one, rollback. So we'll be performing the rollback operations. We'll be undoing certain things. Then rollback, if we go with the rollback, actually this will be, we will undo union of 2, 3, the previous one actually. Then we'll be going with a union of 4, 5, this one. Yeah. So these operations will be performing. It's as simple as that. Yeah. 1 second. Oh, I have not opened this one. 1 second. Damn. I completely forgot to open this. Anyways, so let me say this one again. So let's suppose, let's consider we have 5 nodes. And so these are the operations that we are performing: 1, 2, 2, 3, and 4, 5. So after 1, 2 as well as the 2, 3, we are performing the union on the edge 1, 2 and the 2, 3. The root will remain 1. If you draw the graph, actually, I'll show you the graph. If we draw the graph for 1, 2, and 2, 3, the root remains 1. Yep. And we are going with a rollback. Rollback in the sense, so we will undo this operation, the previous operation. It is nothing but 2 3, right? The edge 2 3 will be deleted, or we are undoing the previous operation. Next we are going with a union 4 5. 1 2 2 3 2 3, we are undoing this one. Let me write here, we are undoing this one. There will be no connection between the 2 3 as we are going with the rollback. After union of 2 3, we are going with a rollback. We are deleting that operation. Finally we are going with a union of 4 5. Union of 4 5 in the sense, yep, union of 4 5 in the sense, we are going with a, yeah, we are going with a union of 4 comma 5. 1 second. Yeah, again we are going with a union of 4 comma 5. So this is fine. Now let's move on with the step by step operations, right? So first we are going with a union of 1 2, right? So this one graph, first initial graph is, we are having 5 nodes, 1 2 3 4 5. All the nodes are isolated, they are not connected to one another. Yep. So this is the initial graph actually. So first step what we are doing, we are going with a union of 2 comma 1 comma 2 actually. So this is the union of the 1 comma 2. So this edge we are connecting, so all other edges remain same. Yep. So this is fine, I believe. Yep. Next, accordingly with the example that we are considering, we are going with union of 2 comma 3. Yep. So this step actually, after union of 2 comma 3, the edge 1 and 2 are connected and the edge 2 3 are connected. Yep. The edge 1 and 2 are connected and the edge 2 3 are connected. Next, we are performing the rollback operations. When I say we are performing the rollback operations, we have to undo the last, nothing but 1 2 as well as the 3. We have to undo the last, nothing but 1 2 this part as well as the 3. See here, when I say we have to undo 1 2, so this one I'm speaking of this one. Yeah, speaking of this one, not undo this one actually, what do we call, undo last one actually. Yep. And when we undo the last operation, the last operation that we had was 2 comma 3, so we will remove this edge completely. Yeah, we will undo this operation means we will delete, so still the edge remains between 1 comma 2 and 3 becomes separated. This edge will be removed, completely removed, right? So you can clearly see the edge is completely removed here. It's as simple as that to understand. It's easier one. Yeah. So next what we are doing, again we are going with the final operation we are performing after union 4 comma 5. So this is 4 comma 5. So again we are going with a union of 4 comma 5, sets the numbers within the same set actually. So this one is connected here this time. Yeah, 4 5 is connected and 1 2 is connected. 3 will be segregated. Yeah, 3 will be segregated, or 3 the edge between 2 and 3 is removed, so 3 gets segregated into the different one, into the different one. Yeah, so the output remains, so this one root of 1 comma 2, so this one for this set actually, if you know the disjoint set union, so for this particular set 1 remains the root actually. Yeah, this one I had said this one earlier, so I forgot to open this one actually. Anyways, for the root 1 and 2, so if we have 1 and 2, the root remains 1. Yeah, uh, root of 1 comma 2 is 1, and root of again this one, when we consider the vertex vertex 1, root of 1 comma 2 is 1, and when we consider the vertex 2, root of 1 comma 2 is 1 itself. Yeah, so this will be 1 1 basically. Now 3 is separate, so I have shown you this one, we had discussed this one. Yep, 3 is separate. Yeah, we have segregated the edges or vertex into 1 2, 3 is separate, and 4 5. Yeah, and 4 5, so that particular edge or vertices. Yep, so 3 is separate, 3 remains same, and root of 4 and root of 5 will be 4 itself. Yeah, it will be 4 and 4 respectively. So the output that we need to get here is according to with the DSU, so 1 1 3 as well as the 4 4. So you have to observe one thing, um, apart from the this one, what do we call, a traditional DSU that we make use of, the one operation that we can perform here by making use of the rollback is it maintains the history of operations. Yep, it maintains the history of operations so that we can just move to the earlier states as well. And with the help of the rollback, what we can do, we can just remove or delete operations as well. Here we have deleted this particular edge 2 3, right? 2 3 was connected, we have completely removed that particular edge, right? So we are going with a rollback operation, so that removes the uh, previous union actually that we had considered. In our case it was 2 3, that particular edge is removed, completely removed. We after that one we got actually 1 2 3 is segregated, 4 and 5 remain same, then we went with a 4 5 union, 1 2 becomes one edge, 3 is completely segregated into the single set, and 4, 5, it will be in the one set. So root of 1, 2 will be 1. Root of 1, 2 for the vertex 1 will be 1. Root of 2 for the this one set 1, 2, it will be 1 as well. Same goes with the 3. 3 is individual. This one, what do we call set? So root of 3 remains 3, and root of 4 for the vertex 4 and 5, nothing but 4, 5, 4, 5 twice. It will be 4 and 4 respectively. So output will be 1, 1, 3, 4, 4. Yeah. So output will be finally 1, 1, 3, 4, 4. This is the output that we need to get if you know the DSU algorithm. If you know the DSU algorithm, it's pretty much it becomes extremely simple to this one. What do we call? Implement this one. All you have to know is we are going with one extra operation rollback that provides undo, or we are able to delete the edge. So that's the huge advantage over DSU, traditional DSU. So we can implement this one rollback operation when it comes to this one. What do we call? Yeah, when it comes to DSU with the rollback. So this is a huge advantage that I wanted to. So this is fine. Now we have to get the output 11344 accordingly with the input that we have considered. And now we know the algorithm as well, how the algorithm works with the union as well as the rollback. So we got the output 11344 because rollback removed the connections between the 2 and 3. So we have discussed this one already. So yeah, so this is fine, I believe. So this is it for the algorithm. It's as simple as that. Now, as we have idea on the algorithm completely, let's do one thing. Let's quickly articulate the same thing that we have written in the form of code. Yeah, let's quickly articulate the same thing in the form of code. If everything goes well and if we get the desired output, then we can discuss the complexities. First, let's discuss let's articulate the same thing in the form of code. Let's do that. So let's do one thing. Let's move on with the further things. First thing, we'll be making use of this one. What do we call? What do we call that? Buffer data as well as the print writer. So I'll just import input output package. So I'll just go with io.star. And also we'll be making use of the different utilities. For that, I have imported the utility package. Next, let's move on with the main coding part. Yep. So within the class DSU with the rollback, first thing that I'll be doing is let's go with the certain global variables. Yeah. So as we are dealing with as we'll be going with the path compression as well as the union and rollback, these three methods. First thing for the path compression, we need parent as well as for this one union method. Within the union method, as we'll be going with the union by size, we need the size variable, and we will be making use of the stack to store the changes for the rollback. Yep. So we need to store the changes for the rollback. So we can perform the undo operation very easily with the stack. That is the main reason we'll be going with the stack. Yep. So these three things. First, I'll just go with static here. So this one is fine. Let me go with int. So I'll just go with a parent. Yep. So this is fine. Next, let me go with a static here. So this one will be int. Let me go with a size. So this is also fine. The third one is nothing but I'll just go with a static here. So sorry, let me write this one in the next line. Yeah. Static. So next, I'll just go with a stack here. Let's make use of the stack. So yeah, we'll be dealing with the integer. So I'll just go with the int. Yep. So this is fine. Yep. So let me go with the history, variable history. Yep. So this is fine. This one remains same. Yeah. Return the syntax correctly. Yeah. So this is fine. Now, first, let's move on with the find method. If you know the DSU, we have to go with the path compression, right? So we'll be finding the root without. So for the rollback, we'll be finding the root without path compression. Yep. So that's the thing that we'll be doing. Yep. We'll not be going with the path compression. Instead, we'll be finding the root without path compression when we make use of the rollback. The main difference between the traditional DSU and the DSU with the rollback. We have to keep this one in mind. So let's move on with the same thing. So I'll just go with int find here. So this is fine. Let me go with the parameter x. So sorry. Within the find method, first thing I'll just go with the while. So let me go with x not equal to parent of x. This one, yeah, x not equal to parent of x. Then I'll do one thing. X, let me assign this one to the parent of x, actually parent of x. So this is fine. Finally, what we'll do, we'll return x. We'll return x. So let me come out of this one entirely. Now let's move on with the union method. So I'll just go with this one static void union. So two parameters that I'll be going with is here A as well as the B. Yeah, A as well as the B. So within the union method, first thing, so we have to find the root of A and we have to find the root of B. If you know this one, what do we call? Disjoint set union. So I'll just give here root A, find of A, and root B, find of B. So after finding the root of A and B, so we have to mark no change. In that case, I'll just write here, if suppose root A equals root B, in that case, what we'll be doing, we have to mark no change, right? Initially. Yep. So for that, I'll just go with a history dot push here new int of, instead of the root A and root B. So let me remove this one. I'll just go with initially, as we are marking no change. So initially I'll keep this one as -1 and -1 respectively. Yeah. So I'll just format the code so that the code looks good. Yep. So this is fine, I believe. What happened here? Why I have closed this one here? So let me do one thing. So I'll just come here. So let me delete this one and I'll just one over here. So yeah, 1 second. Format the code so that the code looks good. So this is fine. Now the next step within the union is nothing but here we have to go with union by size, right? So we have to attach the smaller tree to the larger. That's what we do within the DSU, right? So for that, I'll just write here if size of root A. Yep, if size of root A, if it is less than size of root B, yep, in that case, what we'll do. So we have to consider the temporary variable as we need to swap actually. I'll just go with the int temp equals root A. Same thing, root A equals root B. Finally, root B, we are assigning this one to the temp. So this is when we consider the temp, it's easy to swap, right? So this is fine. Let's move on with the further things. Yep. So we have to save the state before change for the rollback. This one rollback actually. For that, I'll just go with a history dot push new int of. I'll just go with a root A as well as the root B this time. Yep. So this is fine. Let me give the semicolon. So this is fine, I believe. Yep. Let me format this one. Now let's do one thing. So we have to attach the root B under root A and we have to update the size. So this is what we do in the traditional DSU as well, right? So I'll just go with, let's attach the root B under this one, root A. So I'll just go with the parent of root B equals root A. So I'll just change this one. We are attaching the root B under root A actually, not root A under root B. So let me change this one accordingly. And then finally, I'll just go with the size of root A is equivalent to size of root A plus size of root B actually. Yep. So this is fine, I believe. We are done with the union method. Yep. So we are done with the union method. Let's do one thing. So this is same actually. Only thing is we have to mark no change here, right? Initially, as we will be saving the earlier version as earlier this one version as well, so that we can revert if we want to later. So here we are marking no changes by making use of the history dot push. The history is the variable that we have considered, right? Global variable. So then one more thing that we are doing here is we are saving the state before the change for the rollback. So these two things are this one extra things that we are doing within the this one DSU with the rollback that we have to consider. All other things are same actually, right? And one more thing, we are not going with the path compression. Without path compression, we are finding the root when it comes to DSU with the rollback. So this is one of the main this one as well. What do we call difference as well, right? From the traditional DSU. Next, let's go with a rollback method. So we have to roll back the last union. So I'll just go with a not history man. What happened here? 1 second. Did I do anything wrong here? 1 second. Yeah. Let's move with the further things actually. Yep. So I'll just go with the one size of is fine. Did I miss anything? 1 second. Fine, we have given. So this is fine. We have closed this one over here. So I have written the if condition here. So this is fine. Oh, this one I have completely forgotten. After this, we have to stop actually. So let me mention return and let me close the if here itself and let me remove this one. Yeah, bracket misplacement actually. Yep. Now let's move on with the further things. Let's move on with the this one rollback method. So I'll just go with int here. So I'll just go with the last. So this one will be we have to get the last change, right? For that, I'll just go with the history dot pop actually. Yeah. history dot pop. So this is fine. It's as simple as that. You would have already guessed this one. Next, so I haven't written the method name itself. First, let me do one thing. I'll just go with the static void. So let me go with the rollback. Sorry for this, by the way. So this is fine. I'll just close this one over here, right? So this is fine. The next step would be, so we have to go with the no operation case as well. For that, if there is no operation, for that case also we have to go again. So if last of 0, if it is equal to -1, in that case we have to drop. So I'll just give the return. Next, I'll just go with int root b equals, let me go with the last of 0. This is fine. And the next step would be int, let me go with the previous size. So I'll just assign this one to the last of 1. Yep, assign this one to the last of 1. Then what I'll do, let's assign the root a. Let's assign the root a to the parent of root. Yeah, to the parent of. So this is fine. Parent of root b, sorry, not just root. Sorry. Yeah, let me mention here root. We have considered root b as parameter, right? So this is fine. Finally, we have to restore the parent as well as we have to restore the size. For restoring the this one parent, I'll just go with the parent of root b. So let me assign this one to root b itself, not a, as we need to restore the parent, and we have to restore the size as well. So I'll just go with the size of root a. So this one, let me remove plus here. Size of root a will be assigning this one to the previous size. So let me change this one to the previous size. Yeah. So this is it for the rollback method. Actually, it's as simple as that. This is very simple. Yep. So again, there are certain changes. Without the path compression, we are finding the root within the this one, what do we call find method. And in the union, we are just going with this particular one. We are going with a history dot push. These are the two things that we are doing extra, right? Unlike within the this one, what do we call traditional DSU, we would just find the A and B, and then we would check this one, we would swap, and finally we would go with this one, right? So these are the two things that we are doing extra here by making use of the history variable, right? So then we are going with the rollback extra method. Within that, what I have done, first we have to get the last change. For that, I have made use of the last variable here, and we have to go with the no operation case as well. That's one of the important edge cases that we have went with here, this one. And finally, we have to restore the parent and we have to restore the size that we have done here, right? So this is fine, I believe. Next, let's do one thing. I'll just come out of this one entirely. Now let's move on with the main method. So I'll just go with public static void main. Yep. So this is fine. I'll just give here throws exception. Yep, throws exception. Instead of the input output exception, I'll just go with the exception. Yep. So this is fine. So let me do one thing. This is completely related to the input output part and displaying the output accordingly with the input that they have given in the yeah, accordingly displaying the output accordingly. Actually, this we are not solving any problem here. We're discussing the algorithm, right? So let me copy paste the same thing, right? Just give me a second here. So let me do one thing. 1 second. Let me do one thing. I'll just paste this one over here, right? So this is the main method actually. Yep. So yeah, within the main method, I have pasted the code. So this is fine. 1 second. Yeah. So let me explain this one, whatever we have written in the main method. See, we are making use of the buffer reader and the print writer, right? So buffer reader and the print writer, it is completely related to the input output part. Basically, buffer reader acts as fast input and this one print writer acts as fast output actually. Yep. So this is fine. N is 5 because if you remember, 1 second. Where is this one? Yeah. If you remember, actually, we had considered this one 5 nodes. Yeah, I had shown you the example. The same thing actually. 1 second. Not directed graph actually. Okay. So this is the example that we considered, right? 1, 2, 3, 4, 5. Initially, it's not connected. It's completely isolated. The edges are not connected. So this is the graph that we have went with during the this one. What do we call algorithm explanation? The same example that we are going with here as well within the main method. So we are considering 5 nodes. So I have kept n equals 5. Parent equals new int of 1. Size equals new int of 1. So we are initializing the array size with the array size actually for the parent as well as the size. Next, we are initializing the this one DSU basically within the for loop. We have initialized the DSU within the for loop. Next, the example, same thing. We are going with the same example. We are going with a union of 1, 2, meaning we have added this particular edge. Then we are going with union of 2, 3. We have added this particular edge as well. Then we are calling the rollback method. The same example we are considering here. When we call the rollback method, so the previous one was we have added the edge 2, 3. This one will be removed, or we are removing this one. We are deleting this one. So this becomes 1, 2. So we have already discussed this one. 2 and 3 become segregated here. Then so let me delete this one. Then finally what we are doing here, again after 2, 3, we are after the rollback, we are going with a union of 4, 5. Yeah, we are going with a union of 4, 5. So this one I have already shown. This becomes like this: 1, 2, 3, 4, 5, right? 4 and 5, we are going with a union of 4, 5. So this will be connected. Now we are going with a for loop. So this one is nothing but we are printing the parents. For printing the parents, we are going with a find of I plus this one, find of I plus this one. So this is fine. So this is nothing but 1, 2, the 3, the node 3 gets segregated, and this is different. And 4 and 5, we are going with a union. So this is fine, I believe. So let me delete this one. 1 second. So this is fine, I believe. Finally, what I have done, so we are just printing the parents here. Parents in the sense, for the 1, 2, the parent is 1. For the again 1, 2, we have considered for the vertex 1, it is 1, 2. The set we are considering within the same this one, right? Same set actually. So for the 1, 2, it's 1 for the vertex 1. For the 1, 2, again for the vertex 2, it is 1. Then 3, it is different set, and it will be the parent will be 3 itself, or the root will be 3 itself. Then for the 4 and 5, again 4, 5, 4, 5 respectively, the root will be 4. Yep, it would be 1, 1, 3, 4, 4 respectively. The output has to be. So let me do one thing. So I'll just come here and let me hit the run button. Yeah. So this is fine. Why we are getting 3, 3, triple 3, 4, 4 here? Something we have done something wrong actually. Within the coding part, we have done something wrong. Let's check the same what we have done wrong. Here what mistake I have done, here we have to store the child root as well as the this one old size of the parent. So instead I have stored root as well as the root. So this is the correct actually, this is the correct one basically. Yep. So I'll just show you this one. We have to store the size of the this one old parent actually. Yeah, old size of the parent we can say. Yep. So this is fine. Let me format the code so that the code looks good. So this is what we have to do. So this is one thing. And within the rollback, I have to make certain changes. Just give me a second. So that's the only change we need, I believe. So here I have already assigned this one to the last zero and last one. I thought I didn't. Anyways, I have assigned this one to the correct thing itself. So everything is fine. So this is the only thing. So we have to go with the child root as well as the old this one parent size. Yeah. So that one is the only thing that was wrong, I believe. So let me run this one again. Let's check if we get the correct output. Yeah, see here. Now we are getting the correct output. 113 4. Yeah, so which is absolutely correct. So we have discussed by considering the same example during the algorithm explanation, and we have discussed the same thing while taking the example as well within the main method. Yeah. So we have to get the output 11344, and we are getting the desired output as well. Right. So we are done with this part. Yep, we are done with this. But now let's do one thing. Let's quickly discuss the complexities part for the code that we have written. So just give me a second here. 1 second. Yeah. So what would be the time complexity here? The time complexity would lead to big of log n. Yeah, the time complexity would lead to big of log n. So why it is big of logarithmic n? The time complexity I'm speaking of actually. The time complexity would lead to big of logarithmic n per union or find. Yeah, per union bar find. So for the union or the find, it's big of logarithmic n. And what would be the space complexity? See, why it is big of logarithmic n? So we are not going with any path compression within the DSU with the rollback. So to find the parent, we are not going with the path compression. Instead, we are finding the parent in the different way, and we are going with a union by size as well. So no path compression, and we are going with a union of size, which would lead to big of logarithmic n time complexity. Yeah, so this is it for the overall time complexity. So what would be the space complexity here? Space complexity would lead to big of n plus q. Yeah, big of n plus q. You would have already guessed this one. Yeah, so because we are making use of the DSU array, we are going with the DSU arrays within the code. Yep, we are making use of the DSU arrays, and also we are going with the rollback history. Nothing but for the rollback history, we are making use of the stack actually. Yeah. So undo operations, we can easily implement the undo operations, right? Previous operations we have to undo. So for that, we are making use of the stack basically. Just give me a second here. 1 second. So yeah, this is it for the algorithm part. We have successfully discussed entire algorithm along with the complexities part as well basically. Yeah. So we are done with the algorithm, DSU with the rollback. There are certain differences with the traditional DSUs. I had stressed on that. So I had repeated that one multiple times so that we can remember those things actually. Yep. So we didn't go with the path compression. That is one of the thing. And there are certain two things that we had added actually as we are going with the as we have to save the history, so that thing, right? So we are going with the stack just to store the this one previous this one versions actually, in I can put it in that way as well. And one more thing what we are doing, yeah, that we are making use of the stack as well, and we are adding certain two operations within the union that I had showed, and we are going with the extra method, nothing but the rollback. So these are some of the differences apart from the this one. What do we call when we compare that one with the traditional DSU? Yeah, so this is fine. We are done with the algorithm. Now let's do one thing. Let's try to implement the exact same thing in the form of let's try to implement the exact same algorithm within the problem. Yeah, let's consider one problem and let's try to implement the same algorithm. Yeah, let's do it. So let's continue with the problem part. Yep. So here you can just go through the question. I'll be providing the link within the comments, right? So I can just go through the question. So you can just go through the entire question. They've mentioned it in a good way actually. You can understand this one clearly. Yeah, they have mentioned the constraints as well along with the example, one single example. Yeah, you can, yeah, single example. So this is fine. Now let me do one thing. Let me summarize the question so that we understand this one even better. Yeah, we understand this one even better. It will be easier for us to solve the problem. Yep. Let me summarize the question. Just give me a second here. 1 second. Yeah. So first thing here, we have n cities. Yeah, we have n cities here, right? So just remember, we have n cities, and also initially no roads. Yeah, initially no roads. Just remember this. We have n cities and initially no roads. Yep. Each day a new road connects to this one. What do we call? Two cities. Each day, right? For each day, I'll write here one. Each day, new road connects. Yeah. New road, what it does, each day, new road connects two cities actually. Yeah. Each day, new road connects two cities. So this is fine, I believe. So after each road addition, I'll just for the row addition, I'll just write here RA. After each road addition, we must report number of connected components. Yeah, what we have to find actually after each road addition, we have to report number of connected components, right? Number of connected components. I'll write CC for the connected components, and we have to find the size of largest component as well, and size. Yeah, we have to report the number of connected components and size of the large component. That's what we have to find. So this one last sentence. So this is it for the question actually. It's as simple as that. Yeah. So let me read this one out loud. Just listen to this carefully. So first thing, we have n cities. Yeah, we have n cities and initially with no roads. Yeah, we have n cities initially with no roads. Yeah. So each day a new road connects two cities. Yeah, each day a new road connects two cities. Yep, we have n cities and initially no roads. Each day a new road connects two cities. After each road addition, after we go with this one, successfully add the road actually, or after each road addition, what we have to do, we have to report this one number of connected components. All we have to do is we have to find the number of connected components and size of the largest component. So this is it for the question. It's as simple as that. Yep, it's purely DSU based problems. You can solve this one easily using the DSU, and as we need the deletion, we'll be going with the rollback. Yep, nothing but DSU with the rollback algorithm. We'll be implementing the entire DSU with the rollback that we had discussed within this problem. Again, so I'm stressing on that. For one last time, let me read the question. So here we have n cities, this one with no initial roads. each day a new road connects two cities. Yeah, each day a new road connects two cities, this part. Yeah, so this is fine. So after each road addition, what we have to do after each road addition, one second, yeah, after each road addition, all we have to do is we have to report number of connected components and size of the largest component. We have to find number of connected components and size of the largest component after each road addition. That's what we have to do. Yep. So this is it for the question. Let me delete this one. Yeah, this is it for the question. So strictly within the this one question, they have mentioned this one constraints. N and M has to be greater than or equal to 1 and less than or equal to 10 to the power of 5. This is fine. And M it has to be greater than or equal to 1 same, and but less than or equal to 10 into 2 into 2 to the 10 to the power of 5, sorry, 2 into 10 to the power of 5, and the values a and b. Yep. So that we have to it has to be greater than or equal to 1 and less than or equal to n, actually, that we consider, right? So this is what the constraints that they have given. Now let's do one thing. We have the understanding of the question completely. Yeah, we have the understanding of the question completely. Let's do one thing. Let's discuss the approach. Yeah, let's discuss the approach, and then after discussing the approach, let's try to articulate the same thing. Whatever we will be discussing the approach, let's try to articulate the same thing in the form of code. If everything goes well and if we get the desired output, then we can just discuss the complexities for the code that we have written. First, let's discuss the what do we call that? Yeah, first let's discuss the approach for the problem. Let's do that. So let's do one thing. Let's continue with the same, actually. Yep. So first thing, I have considered the same example for the approach. So whatever they have mentioned in the, or whatever they have given in the question, the example 5 3 1 2 1 3 as well as the 4 5, wherever I have pointed the this one. Mouse, actually. See here, 5 3 1 2 1 3 and 4 5 is the input that they have given, right? So I have considered the same thing, right? So we will be making use of the disjoint set union with the rollback. Yeah, we'll be making use of the disjoint set union, DSU, or the union find with the rollback. One second, what happened to this? Yeah. So this is what we will be making use of, right? So this is fine. First, what we'll do, if you know the disjoint set union, we will track the parent of each node. Yeah, we'll track the parent of each node. Then size of the each component. Size of the each component, we'll be writing for that within the union method, basically. Tracking this one parent of each node, that will be done within the find method, right? So we'll be going with this one. We'll be finding the root without this one, what we call path compression, as we are going with a DSU with a rollback. Yep. So the next one or the final one is nothing but we will be merging the components efficiently, right? After these two processes, we have to merge, right, within the DSU. So we'll be accordingly with the sets that we had considered. So we will be merging the components efficiently, right? So this is fine. Then what we'll do, basically, let's consider the day one. Day one, we have to add the edge one as well as the two. These are the edges, actually. So this is nothing but the number of nodes or the vertex 5. Yeah, I'll just write V or N. Let's consider N. Yeah, number of nodes, and this is nothing but the number of edges. Yeah, number of edges. We have three edges, 1 2 1 3 as well as the 4 5, and number of nodes is we have 1 2 3 4 5. Sorry, yeah, 1 2 3 4 5. Yeah, we have 5 nodes, actually. Yeah. So basically, yep. First, let's consider 1 2 on the day one. So we will add the road 1 2, nothing but we'll be adding the we'll be connecting the cities, basically 1 and 2 respectively, right? So we'll be adding 1 and 2. So initially we have 1 2 3 4 as well as the 5 respectively. What we'll do, we'll merge 1 and 2. We have to merge 1 and 2. So 1 and 2 becomes same, right? 1 and 2 will be present in the same set, actually, if you know the disjoint union set. Sorry, yeah, disjoint union, actually. Yep. So here we will be merging 1 and 2, and 1 and 2 will be present in the same set. Now we have the 4 components left, and the max size is 2, and the max size is 2, because we have components 1 and 2 respectively, and components is 4 and max size is 2. Let's come to the day 2 here. Day 2, we have to connect 1 and 3 accordingly with the input. Yeah, 1 and 3. So now we'll be adding the road 1 3. First, let me show you the graph. So this is the initial graph, actually. Yeah. So every node is isolated and it is not connected to one another. Yeah, the nodes are not connected to one another. After day one, we have successfully added 1 2, right? So after day one, we have successfully added the edge 1 2. You can clearly see here this part. We have connected 1 2. All other nodes remain same. They're still not connected. Yeah. So now we have moved to the day 2 part. where we are adding edge 1, 3 accordingly with the input or the example that we have considered. Now 1 belongs to 1, 2. Yeah, 1 belongs to 1, 2. So this part 1 belongs to 1, 2. So we will merge 1, 2 as well as the this one. What do we call 3? Right. So we'll be merging as 1 belongs to 1, 2. So the digit 1 belongs to 1, 2, the set 1, 2, right? So we will be merging 1, 2, and 3. So after merging 1, 2, this one 1, 2, and 3, so 3 will be present in the same set as 1, 2, right? So it will be the digits are or the numbers will be 1, 2, and 3. So this particular set consists of the numbers or the digits 1, 2, and 3 like this. See here, as 1 belongs to the 1, 2 actually. So we will be merging 3 to the same actually. Now the graph becomes like this: 1, 2, 3, and 4 and 5 are still not connected. Yeah, 4 and 5 are still not connected. So this one, after the step 3, after adding the edge 1, 3, after day 2, after adding edge 1, 3, the graph is shown in this way: 1, 2, 3, as well as 4 and 5 are still not connected. Yeah, we are left with the last day, nothing but the day 3. Accordingly with the example, see, we have to connect the edge 4 and 5 respectively. Yep. So we have to connect the edge 4 and 5 respectively. Now what we will be doing for connecting the edge 4 and 5. So first we have to add the row 4 and 5. So we will merge 4 and 5. Right. So we have 1, 2, 3 within the one set. So now we this one 4 and 5 this one still not connected. So what we'll do, we will merge 4 and 5 into the different set. Yeah. If you know the algorithm DSU, we will be merging 4 and 5 into the different set. So now 4 and 5 will be present in the same set actually. 1, 2, 3 different set, 4 and 5 in the different set. Now the components are 2 actually, and maximum size is 3. Maximum size is 3. Here the components were 3 and maximum size 3. This one I entirely forgot to mention. Components last one you can just check, components 3 here and maximum size also 3. You can clearly see 1, 2, 3, right? Components 3 and maximum size we are getting 1, 2, 3, 3 itself. So here components are only 2 actually, 4 and 5. Maximum size from the previous one, it remains this one 3 itself, right? So but we have only 2 components. So components is 2 and maximum size is 3. So the last one becomes like this. So 1, 2, and 1, 3. This is one set actually. I can just call this one as set 1. So this one 4 and 5 is now connected. I can just call this one as set 2. Yeah, the set 2. Yep. So let's move on with the output explanation. So day 1 we have the components 1, 2, 3, 4, 5, where largest size is equivalent to the 2. So you can clearly see this is the largest size. We are going with the size, right? So we are going with the size, not the this one digit, largest digit here. The largest size is, this set consists of the 2 elements. So the largest size is this one 2, and the output is nothing but 4, 2, right? Output is nothing but 4, 2. Yep. So we are going with we are going in this way. The output is nothing but 4, 2. After within the day 2, the components that we have is 1, 2, 3 as well as the 4, 5, right? So this one 1, 2, 3 is connected. So this belongs to set 1, and 4, 5 is still not connected. Yeah, 4, 5 is still not connected. So the output will be, so this forms 3 actually. So the largest component here, so this one size also, this is nothing but the size, don't get confused here. This is size and this is the largest, this one size actually. Overall size is nothing but here, this is 1, 2, 3, 4. We have 4 sets, and this one, what do we call? Output is nothing but 4, as well as the largest size that we got is 2. Both we have to display both accordingly with the question that they have given. So 4 and 2 respectively for the day 1. Components now we have 3 actually. 1, 2, 1, 2, 3. 3 sets, and we have this one, what do we call? The largest set size actually. You can clearly see here, this set consists of the 3 elements. So the largest size would be quite obviously 3, right? The largest size would be quite obviously 3. So the size we have displayed, and along with that the number of this one sets that are present, that also we have to display, nothing but 3. The output will be 3, 3, and for the day 3 the components are nothing but 1, 2, 3 as well as the 4, 5. This forms one set and this forms 2 set. We have already written this one. Yeah, 1, 2, 3 as well as the 4, 5. See, 1, 2, 3 as well as the 4, 5. So this is set 1 and this is set 2. So we have 2 sets. So the output for the number of sets is 2, and the largest size you can clearly count the digits that is present in the set 1, nothing but 1, 2 as well as the 3 respectively. Here in this case the output will be 3. Yeah, in this case the output will be 3. So the output total the output will be 2 and 3 respectively. So for the first one it is 4 and 2. For the first one, the output is 4 and 2. And for the second one, it is 3 and 3. For the second one, it is 3 and 3. For the third one, it is 2 and 3. For the third one, it is 2 and 3. So this is the overall output that we need to get accordingly with the approach that we have considered. Accordingly with the DSU, we'll be performing the DSU, and I have shown you this one graph. I have shown you the entire approach, and I have shown you the output explanation by considering the this one same example that I've given in the question. Sorry, the output that we need to get here is 4 2 3 3 as well as the 2 3 respectively. So this is it for the approach. It's as simple as that. If you know the disjoint set union algorithm, it is completely easy. Yeah, it's a piece of cake to implement. Yep. All you have to do is you have to know the DSU algorithm, and we will be going with the rollback. Rollback supports deletion or the undo operation. Yeah. So within the algorithm, we had made use of the stack to go with the undo operation. Yep. So on the difference I had stressed already. Let's brush up actually. Let me tell this one again, or let me stress this one again. So we will be finding the root without path compression within the find method. That's the huge difference, first difference. And we'll be performing two extra operations within the union method. So we'll be going with the union by size or union by rank. We call it as union by rank or union by size. Actually, in here, the union by size, that would be the correct term to use. Actually, we'll be going with the union by size. And the rollback, within the rollback, actually, we will be storing the history, the version history, right? So that we can roll back to the or we can just go back to the previous versions as well. We can revert to the previous versions as well. So that's where a revert method comes. This one plays a prominent role. Actually, we can delete, undo, and that will be saved in that will be saved as particular version actually. Yep. So this is fine. Now, yep. This is it for the approach actually, and these are certain differences when we compare DSU and DSU with rollback. Yeah, when we compare the DSU with the rollback with the traditional DSU. Now we are done with the DSU with the rollback algorithm. We are done with the approach part basically. Now let's do one thing. Let's try to articulate the same thing in the form of code. Let's do that. Let's try to articulate the exact same thing in the form of code. And if we if we get the desired output, if everything goes well and if we get the desired output, then later we can just discuss the complexities for the code that we have written. First, let's do one thing. Let's discuss the what do we call? Yeah, let's articulate the same thing in the form of code, whatever we have discussed in the approach part. Yeah, let's do that quickly. So let's do one thing. Let's start writing the code. Yep. Let me minimize this one. Let me close the algorithm part. Let's come to the problem part here. Sorry. Yeah, let's continue writing the code. So yeah, first thing, we'll be making use of the buffer reader as well as the print writer. So let me import here java dot input output. Let's import the input output package actually. So yeah, within the class road construction, this one CSES. So this is the problem we had considered from the CSES, right? So let's do one thing. Let's write. Let's declare certain global variables here. So we will be going with a parent actually static int parent for the this one. What do we call? We'll be making use of the parent, right? So within the find basically for that. So we have to go with the rank as well. Within the union method, we'll be going with the union by rank basically. Usually we call it as union by rank or union by size. So I'll just go with the rank RNK. So this is fine. So this one has to be int as well. So I completely forgot the int. Next, let's do one thing. So we have to go with a size array, nothing but we have to store the size of each component. For that, I'll just go with a static here int. Yep. So let me go with the size. So this is also fine. Next, let's go with the variables so that we can, so we should be able to track the current number of components and the maximum size. For that, I'll just go with the static. So let me go with the int here, components. So this is also fine. Let me go with the maximum size. Yeah, let me go with the maximum size. So I'll just go with maximum size. So this is fine. Yep. Next, what are the things that we have considered? Components in the max size, right? So this is fine. Now let's go with a find method. Yep. So I'll just go with static int find. So this is fine. I need the parameter x actually. Yep. So the same thing. So we have to find the root of the node, right? So no path compression, just for the simplicity, as we are making use of the DSU with the rollback. So I'll just go with while. So this one will be parent of x. Yep. If that is not equal to x, in that case, so let me do one thing. I'll just go with, let me assign x equals parent of x actually. Yep. So this is fine. Next, what am I going to do? All we have to do is we have to return root, nothing but return x. So I'll just come out of this one entirely. Next, let's go with a union function or the union method. Basically, within the union method, we'll be merging two components. Yeah. So I'll just go with the static here. Yep. Static. I'll just go with a void. For the union, I'll just write here unite, union. Yeah. So both are same. So I'll just go with the int a and b as parameters. So we have to find the root of both nodes, right? A and b basically. So I'll just go with here a equals find of a as well as b equals find of b. So this is fine. So if they are already in the same component, already in the same component or the same set actually, the digits. So then we don't then we shouldn't be doing anything in that case. So I'll just go with if a equals b, then we have to stop actually. For that, I'll just make use of the return statement. So we have to make sure that the higher rank root becomes the parent, right? So that is the reason we are making use of the disjoint set union. For that, I'll just go with if rank of A, if it is less than rank of B. So instead of greater, I'll just go with a less than symbol here. If it is less than rank of B, in that case, let's make use of the temporary variable. I'll just assign this one to A and A to B. And finally, I'll just do one thing. Let me assign B to T. Yep. So this is fine. Let's move on with the further things. Let's attach B under A, right? So I'll just go with the parent of A to the B. We have successfully attached B under A. Parent of A, sorry, parent of not A to B, parent of B. Actually, we have to attach the B under A, right? So this is fine. And after that, we have to this one update the size of the new component. We have considered for the size, we have considered SZ, the variable SZ, size of A equal size of A plus size of B. So this is fine. Next, if the ranks are same, we have to increase the rank of the root. For that, I'll just go with if yep, instead of size, we are considering rank, right? If ranks are same, actually, I'll just go with a rank of A if it is equivalent to rank of B. Yep, in that case, what we have to do, we have to increase the rank of the root actually. So I'll just go with rank of A. For incrementing, I'll just go with the plus plus. Yeah. So let me remove this one. This is not required. Yeah. So this is fine. Next, what we are going to do next? So we have to decrease the number of components, right? So we will be merging 2 into 1 basically. For that, we have to decrement the components, nothing but components minus minus. Finally, we are left with only one thing within the unite method. We have to update the maximum component size. For that, I'll just go with if, let me go with size of A here, size of A. If it is greater than max size, suppose if it is greater than max size, then max size, let me assign this one to the size of A. Let me assign this one to the size of A. 1 second, just give me a second here. Yeah, let's continue with the same here. So if size of A greater than size, this one max size, then we have to update the max size, right? So we have to assign this one to the size of A itself. So this is fine. So let me do one more. Anyways, now let me format the code once here. So this is it for the unite method. Next, let's move on with the this one. What do we call? 1 second. So we have written this one rollback within the unite method itself, right? So this is fine. Let's do one thing. Let's write whatever that is related to the input output part. Let's write that one within the main method. Let's do that very quickly. Yeah. Let me copy paste that one as it is completely related to the input output. I'll explain that one. Yeah. So that's fine. So I'll do one thing. This is pure incremental, I think. The solution that I took basically. Yep. So let me do one thing. I'll just paste this one over here. So there are certain changes that is required. Let me paste the code entirely. So there are certain changes. I have went with a pure DSU with the incremental. Yeah. So let's go with a rollback rather than the pure DSU, right? So let me paste the code. So I could have made the necessary changes. I would have typed actually changes. That doesn't make sense now. So let me this one, delete this one entirely, and let me paste this one over here. Let me explain the code actually. Yeah. So this is fine. What happened here? This is fine. Yep. So let me explain this one from the beginning. So first thing here, what we are doing, we are going with certain global variables here. So here, parent is nothing but here in this case, parent rank and size. Parent rank and size nothing but we are going with a parent array. One second. So we were going with the correct path itself. The this one, the path that were going with actually, it was plain DSU. And instead, I wanted to go with a DSU rollback actually. That is the reason I have this one. It tweaked a bit in the code. Yep. So we can just go with a just traditional DSU or the incremental one. So that works as well, right? So we don't have to go with a rollback. So if we implement the rollback, this is one of the best problems to go with the DSU with a rollback as well, right? As we have discussed the DSU with a rollback algorithm, I have implemented, I have changed the code. So let me explain you this one step by step. So this one parent rank as well as the size, whatever I have considered. So this PR is nothing but the parent array, rank is nothing but the rank for balancing, which we will be writing within the union method, and size is nothing but the size of the component. Next, we are going with a history U as well as the history V, nothing but these are the history arrays to store the nodes involved in the union. As we are going with the rollback, we will be saving the this one version history, right? So the previous versions actually. Yep. So this is fine. History rank U, history size U, as well as the history size V. This is nothing but these are we have to store the previous rank and sizes for the rollback. That is the reason we are considering these variables. Next, we have considered history top. History top is nothing but it is the pointer to current position in the history stack. Finally, we are going with the components as well as the max size. Components as well as the max size. See, we have to track the number of components and the largest component size as well. For that, we have considered these two variables. So this is fine, I believe. Next, let's move on with a find method actually. Within the find method, as we are going with a this one, what do we call DSO with a rollback, we are not going with a path compression, right? So inside the find method, we have just considered the parameter x. So we have to keep moving to parent until the root is found. If you know the this one DSU algorithm, yeah, that's what we'll be doing within the find method. The only difference is we'll not be going with the path compression as we are going with the DSU with the rollback. Now return x is nothing but we are returning the root representative or the parent. Next, let's move on with the unite method. Usually the DSU method, we will be going with a union, right? So this is nothing but same actually. Instead of the union, so I have went with a this one method name unite. Yep. So as usual, if you know the algorithm A and B, we are just finding the root of node A as well as we are finding the root of node B. So if A equals B, we are going with a history of history top plus plus. This we are setting this one to the -1. See, suppose if both nodes are already in the component, we have going with this particular method, right? Suppose if both nodes are in the already in the same component, we have to mark that operation as no operation in history, right? So no operation in history. For that reason itself, history U of this one history top plus plus, we have assigned this one to the -1, as we need to mark this operation as no op in the history. If you know the algorithm, we did the same thing within the DSU with the rollback algorithm as well. Finally, we have to stop here. So I have made use of the return statement. Let's move on with the next if condition here. Next if condition, we are going with the rank A. We are checking whether rank A less than rank B, nothing but we are ensuring A has the higher rank, right? So that is the reason we are going with a DSU, right? Union method basically. So we are checking or we are ensuring A always has the higher rank, and we are swapping A and B. For swapping A and B, it's easy to swap by considering the temporary variable. So T is nothing but the temporary variable. This is the swapping part actually. After successfully swapping, I have went with certain variables. Let me explain you this one step by step. So history of U of history top, history U of history top, we have assigned this one to A, nothing but we are storing the A in history. Yep. And we are also storing the B in history, right? So the next one, we have to store the previous rank of A. We have to store the previous rank of A. That we have done with by making use of the history rank U. We have we have considered or we have passed history top, that we have assigned that one to the rank of A basically. After the same thing we are doing it for the this one, what do we call? We are storing the previous rank of A. This is fine. Sorry. So this one history size U of history top, we have assigned this one to the size of A, and history size of B, history of top, this one we have assigned this one to the size of B. Nothing but we are storing the previous size of A and B within these two lines. Yeah, we are storing the previous size of A and B. Then finally history top plus plus we are incrementing here, right? So this part. So this one we are moving the history point forward, right? So this is fine, I believe. Next, what we are doing, so we are assigning the parent of B to A, nothing but we are attaching the tree of B under A. We have to attach the smaller one under the larger one, right? If you know the algorithm. So we are attaching the this one, what do we call? Tree of B under A. Next, we are updating the size of the component A, pure this one, DSU with the rollback algorithm. After this one, updating the size of the component. So we have to check, suppose if the ranks were equal, we have to increment the rank of A in that case. Yeah, size of the rank. So this one, rank of A and rank of B, we are keeping the rank of A always higher than the B, right? And then we are attaching the B, then we have to attach the B under A, right? Rank of the A has to be always higher, right? So for that, we are checking the condition. Suppose if the ranks were equal, then we have to increment the rank of A and reduce the number of components since 2 merged into the 1. Since 2 merged into the 1. Finally, we have to update the maximum component size. Yeah, accordingly with the question, they have asked us to this one, what do we call? Go with the maximum component as well. Yep, maximum component along with the size. With this one maximum size, we have to mention the numbers present in the set as well, right? So we are updating the maximum component size here, right? Suppose yeah, if the size of A, if it is greater than the max size, we are assigning this one to the size of A. This is pure updation. Yep. Then let's move on with the rollback method. Rollback, we have only one parameter, nothing but the target. Here, history top, if it is greater than the target, suppose history top, if it is greater than the target, then we have to move back in history. For moving back in history, we have considered the history top actually. I'm just decrementing that variable. It's as simple as that. Now, we are going with this one, int A. We have assigned this one to the history U of history top, nothing but we, yeah. So we have to get stored root A. Then if it was a no operation union, then we have to skip. For that reason, I have we are checking this one. If A equals -1, we have to skip that step, right? So finally, we have to get stored root B as well, similar to the A here, history U of history top. The same thing we have done for the B as well. So here after that, so we have to restore the parent of B. For that, I have assigned parent of B to B. So last 3 steps, whatever, last 4, this one lines, whatever I have written, rank A equals history rank of history top. We are restoring the previous rank of A. Then we are restoring the this one, what do we call? We are restoring the previous rank of A, then we are restoring the previous size of A and B here, right? So this is fine. Later or finally, we have to increase the component count since merge is undone. So merge is undone yet. So we have to increase the component size here. That is the reason we have considered the components variable and we are incrementing the components here, right? So this is it for the rollback. So and this is it for the implementation part as well. So we were writing the or we were implementing the pure DSU. I took this code actually. So this basically I forgot for a second that we are going with the rollback actually. The algorithm that we had considered, we had discussed is nothing but DSU with a rollback, not the traditional DSU. Traditional DSU, we have already considered that one within the 150 based algorithms playlist, and you can just go through that this one, that algorithm if you want to. If you know the DSU algorithm, implementing the DSU with rollback actually, it will be a piece of cake. There are only certain tweaks or changes that is required, and you should be or you will be able to do that. Yep. Once you know the DSU algorithm, DSU with the rollback will not be a will not be difficult actually. Only one difference is so we'll be maintaining the stack within the algorithm, not the problem I'm speaking. If we will be going with the stack because we will suppose if we want to delete, it supports the delete operation, rollback or undo operation. For undoing, so we'll be maintaining the stack. It's easy to undo by making use of the stack. So we'll be going with the stack. That's it. Yeah. Now let's move on with the main method. Within the main method, so we are going with the buffer header as well as the this one, stream tokenizer. Buffer header and stream tokenizer. So buffer header is for the fast input and stream tokenizer is for the fast output. Yeah. So this main method, I always write it on this. My main method, usually this is completely related to the input output part. Yeah. So next, after the buffer header and the stream tokenizer. So this is basically tokenizer for the fast parsing. right? So we are considering this one for the fast passing actually. So in dot next this one token, we have to read the next token and we have to read the number of cities accordingly with the question. So I'll just open this one. We have to read the number of this one first line actually. Yep, number of cities, right? So this is fine, I believe. We have to read the number of cities actually. This is nothing but we are reading the number of cities. Yep, this one, line number 65 actually. Yeah. Then we have to read the next token again, similarly to this one, and we have to read the number of roads as well. Number of roads here 3, right? So number of cities 5 and number of roads 3 actually. Yep, nothing but number of vertices 5 and number of edges 3. Yep. So this one we have to read the entire first line. So we have done that one. This one. Yep. After successfully reading this one, what do we call number of cities and number of roads? So we have to initialize the parent array, rank array, as well as the size array, as we are making use of the this one union, Disjoint-Set-Union, DSU. So that's what we have done here, right? So the next we have went with a for loop. Why we are going with a for loop? We have to loop through all the nodes, right? We have to check whether each node is its own parent initially, and each component has size 1 initially. For that one, we have written the for loop. So let me leave the space so that we don't get confused. This is fine. Next, we are going with certain this one here, certain variables. Let me explain this one clearly. So we are going with a history max equals m plus 10. Why we are going with m plus 10 here? So this is the maximum size for the history arrays. Yeah, this is the maximum size for the history arrays. Then we have already declared these variables actually. Why we are making use of it again? So we have to allocate the history array for the root A and B that we have done in the first two lines, 79 and 7, this one 80. Then we have to allocate the history for the rank, and we have to allocate the history for size of A and B that we have done with the next 3 lines. We have successfully allocated history for rank, history for the size of A and B respectively, and finally we have to initialize the history point as well, history pointer that we have done here, history top equals 0. It's as simple as that. Now let's move on with the further things. Components equals n and max size equals 1. These two things. Components equals n because initially all nodes are separate components. So we have assigned the components to n, and initially the largest component size is 1. So maximum size we have assigned this one to the 1. So finally we are going with a string builder. String builder, so this is for the fast output. For the fast input, basically we have considered the buffered reader. So where is it? The main method, first line, buffered reader. So we have to read the stream of tokens. For that, we have went with the stream tokenizer. We have to go with the fast output as well. For the fast output builder, we are going with a string, this one, string builder. So for loop, because we have to process each road. Yep, we have to process each road or each edge. So for that, we have considered the for loop here, right? We have to process the each edge or each road accordingly with the question. That is the reason we are going with the for loop here. Within the for loop, we have to read the first city, next token, read the next token, read the first city, then read the next token and read the second city as well. Yeah, vertex, nothing but 2 vertex when we connect into the edge, right? So this is fine. Then we are going with a unite of a comma b. Unite, we have already written the unite method here. This one, usually we call it as union, right? We have already written the unite method. So we are calling unite of a comma b because we have to merge 2 cities. Yep, we have to merge the 2 cities accordingly with the question. We have to merge the 2 cities itself, right? So after merging the 2 cities, what we have to do? So we have to store the result. Storing the result, we are storing the result in the string builder variable sp.append. So what we are appending here, components, and we need space actually within the this one. See here, output 4. After the 4, we have space, right? So we are appending space, and then we are appending the max size. So the number of components that are present in the set actually of that first that we are displaying first. So we had discussed this one during the approach, and then we have to display the maximum size as well, right? So the maximum size also we have to display next to it after the space actually, right? So that we are doing here. See, that we are doing here 4, then 2. Then for the next one, we have to go to the next line, 3, 3. We have to go to the next line, right? For that, I have mentioned slash n here, right? It's as simple as that. Now, finally, we have to print all the results at once. So we are going with a system out print here, right? So we don't have to go with a system out println. Instead, we have to print all the results at once. So we can just go with a system out print here. All we have to do is we have to pass the string builder variable sp where we are storing the output actually. Yeah. So we are done with the coding part. It's as simple as that. Yeah. So let me do one thing. I'll just open the Chrome. Let me copy this one. Yeah, and one more thing, don't get confused here because I copy pasted. So I had written until this one, unite, basically find and unite, which is the this one, pure DSU implementation. So I wanted to go with a DSU with a rollback, as we had discussed the rollback, a DSU with a rollback algorithm itself, rather than the traditional DSU. That is the reason I copy pasted the code. There are I would have changed the code there itself, but it would have led to the confusion. So I pasted the code. I had already solved this one. So I have pasted the code, and only for this particular problem, I have pasted the code and I have explained you guys. Yeah, or we have discussed actually. Apart from that, yeah, we have considered certain this one from the traditional uh, apart from the traditional unlike traditional DSU, we have went with certain variables, history u, history v, these kind of variables. These are extra variables basically. We have basically DSU with a rollback maintains the version history as well, right? So for that we have went with these variables. That's it. The one that is linked with a HIST, right? Yeah, prefix HIST, nothing but the history, whether it may be history top, history rank u, size uv, yep, history uv, these kind of things. Yep. So only one thing here, see, this step is extra as per the algorithm. I had explained you this one. This step is extra. And one more thing, these things we have mentioned, this one, history, as well as this method is extra. Yeah. So we can just go with the incremental DSU as well, right? Or the traditional DSU. That works as well. So, but this is one of the best problems that I've found to implement the DSU with a rollback, right? So this is fine. So we have went with a rollback here. This is fine, I believe. So I have explained you this part, and I have this one main method consists of this one entirely. This is related to the input output part and how we need to display the output actually, right? So we have to read the input. We have to read the input that they have given in the this one, what do we call question, and we should be able to display the output uh, as per the as per their requirement actually, right? How they have given in the this one question, they have mentioned in this way we have to display the output. So that we have done within the main method. So I have explained you this one correctly. So this is fine. We are done with the problem part actually. We are done with the problem part. Let's do one thing. Let's try to submit the same code. Let's see whether this code works or not. So I'll just open Chrome. There is something called submit button here within the CSS. So I'll just click the submit here. So I'll just go with this one language. Let me select Java here. So you can clearly see here Java. So let me hit the choose file. So I'll just go with a desktop here. One second. Let me go with this one src. So I'll just go with the main here. Yep. Let me open the Java. I'll just open org here. One second. What happened to this one? Just give me a second here. src. I'll just go with the main. Java. So yeah, here you can clearly see we have the DSU with the rollback algorithm. Yeah. So within the DSU with the rollback algorithm, so let me submit this one, road construction css.java. So let me select this one and let me open this one over here. Warning, don't use package in your code. Okay, yeah, I had to remove that one. Yeah. For now, let me do one thing. Let me remove this one, or let me this one uncomment this one. So this is not required for the during the submission actually. I'll just come here. Yeah. Let me select this one again. So I'll just consider one second. Not this one. Yeah, this one actually. Yep. Let me open. Then let me hit the submit. Let's wait for some time. I can clearly see here testing. See here, we have got the result accepted, or yeah, we have got the verdict or the result accepted, meaning whatever the code that we have written works absolutely correct here, right? So this package, this one, this is only for the IntelliJ, right? So this is fine. Whatever the code that we have written works absolutely correct, and you can check the test cases as well here, right? So this one, correct output along with the test second test, third test, right? So I can just check the test cases as well. So whatever the code that we have written works absolutely correct. We have went with a pure DSU with the rollback implementation here, right? Initially, I started with a traditional DSU. I forgot that we are going with the DSU with the rollback. So yeah, so this is fine. Finally, we have implemented the DSU with the rollback. Yep, a DSU with a rollback algorithm implementation within this particular problem. So this works flawlessly actually. Yeah, we are getting the this one result of the verdict accepted. So whatever the code, again, sorry for repeating, whatever the code that we have written works absolutely correct for this particular problem. So this is fine. Yep, we are done with the coding part actually. Yep, we are done with the coding part. Now let's do one thing. As we are done with the coding part, we are left with only one thing, nothing but discussing the complexities for the code that we have written. Yep, let's do that quickly. So this is fine, I believe. Let's do one thing. Where is it? So I'll just do one thing. So let me select this one over here. Yeah. 1 second. Yeah. What would be the time complexity here? Time complexity would lead to here because of this one m into n actually. Yeah. Because of m into amortized for amortized. I'll just write here the small value actually. It will be because of m into amortized of n actually. So this will be almost equivalent to big of m itself. We can consider big of m directly. The time complexity is almost equivalent to the big of m because we are making use of the unite as well as the find method, two methods, right? So both of the methods runs in almost constant time, right? So this is nothing but inverse Ackermann. So not amortized, sorry, inverse Ackermann of n. So this one a, right? I forgot the term itself. Yeah. So this is nothing but big of m into inverse Ackermann of n. So it's almost equivalent to the big of m. You can just consider this one as the time complexity big of m actually. Yep. So what will be the space complexity then? Space complexity you would have already guessed. Space complexity, it is simply big of n plus m. Yeah. Simply it is big of n plus m, or we can just go with a this one and big of n for the DSU arrays. So this is big of n actually. See, big of n plus m. Sorry, how it is big of n plus m? So it is big of n for the DSU arrays. So we have went with the DSU arrays, right? So I'll just mention here DSU arrays. For the DSU arrays, it is big of n. Big of m is for the rollback history storage. We are storing the history, right? So we are storing the. We can just call that one as version history, or it is big of m for the rollback history storage. So overall space complexity would lead to big of n plus m here. So the time complexity for the code that we have written would lead to big of m and big of n plus m. You can just ignore this one. This is nothing but small value. Big of m into inverse Ackermann of n actually. Yeah, usually the small value will be representing that one in the form of inverse Ackermann, right? So it would be big of m into inverse Ackermann of n. That is almost equivalent to big of m, and the space complexity would lead to big of n plus m. Yep. So this is it for the time complexity as well as the space complexity. Yep. For the code that we have written. Finally, we are done with the coding part and we have discussed the complexities as well. Yep. Now, yep. Now we are done with the what do we call DSU with the rollback algorithm, and this is the last algorithm within the dynamic graph algorithms playlist. Yeah, advanced or complex dynamic algorithms graph algorithms playlist. So this is the last algorithm actually, and yep. So we have successfully discussed this one and discussed the algorithm, and we have implemented the DSU with the rollback algorithm within the problem as well, and we got the verdict accepted, and we have discussed the complexities part as well. We have discussed everything entirely, right? So we have got the opportunity to implement the algorithm within this problem as well. Now, from tomorrow, I'll just go slowly. If I get time, I'll just upload every single day. If I don't have time, I'll be going slowly. Yeah. So next, what we will be doing, we will be discussing on the this one. What do we call DP algorithms? Yeah, complex DP algorithms. Yeah, as I've said, we have entire year for this one, discussing the algorithms. Actually, let's go very slow. So if I have time, so I'll just go this one. I'll just upload a single this one algorithm and let's implement the same thing every day. Let's do the same thing for the this one complex or the this one. What do we call advanced DP algorithms? Yeah, hard DP algorithms basically. Yeah. So what are the algorithms that we will be discussing? Let me mention now itself. Just give me a second here. So yeah, what are the algorithms that we'll be discussing under this one? Hardcore DP algorithms or complex DP algorithms? See, SMAWK algorithm, SMAWK algorithm. So this is one of the algorithms. So then subset convolution algorithm, which is one of the well-known algorithms, divide and conquer DP algorithm. So that we will be discussing. Knuth optimization, it's one of the this one. Very well-known algorithms as well. So Monge DP, this one optimization, that also we'll be discussing. Quadrangle inequality DP, that is also one of the well-known algorithms actually. Alien strict, so alien strict usually we call it as parametric DP, right? So that parametric DP we also call it as alien strict actually. That algorithm also we'll be discussing. So that's one of the very well-known algorithms as well. So we'll be discussing alien trick or the parametric DP. So that's one of the algorithms that we'll be discussing. Broken profile DP, that is also one of the well-known algorithms that we'll be discussing. And SOS DP, that's also one of the algorithms that we'll be discussing. Finally, we'll be discussing bitset DP optimization algorithm as well. So it's well known when it comes to extreme optimization, bitset DP optimization. So these are some of the algorithms. So again, 2, 3, 4, 5, 6. Here, total 10 algorithms we'll be discussing. Again, SMAWK algorithm, SMAWK, subset convolution, divide and conquer DP, Knuth optimization DP, Monge DP optimization, quadrangle inequality DP, alien strict or the parametric DP. You would have heard of parametric DP. So we call that one as alien strict as well. So broken profile DP, that's one of the well-known algorithms as well. SOS DP, which is one of the well-known algorithms. Finally, bitset DP optimization. So these are the 10 algorithms that we'll be discussing under hardcore dynamic programming algorithms or complex dynamic programming algorithms. Yeah. So I hope today whatever we have discussed, this particular algorithm, DSU with the rollback, and whatever the implementation that we have done within the problem is completely clear, right? I hope it's completely clear, right? So for now, this is it. And one more thing, before that, I want to tell you that I'll be uploading these 5 algorithms within the GitHub as well. Yeah, you can just check the problems that we have solved along with the algorithms, along with that the problem that we have implemented actually, basically where we implemented that particular algorithm. Both I'll be this one uploading within the GitHub. You can check there as well, right? So yep, for now this is it. Thanks for watching, guys.